All right, we're recording. All right, last lesson of chapter 1, composite objects. Okay, what do we mean by composite objects? Well, what we mean is, three-dimensional objects comprise. Notice comprise and compose kind of have the same prefix. Comprise, that means made up of. So 3D objects made up of regular 3D. I'll use this word. I don't think I've used this word yet. Polyhedra. And that just means regular many-faced objects. Right? Polygon means many-sided. Polyhedra means many-faced. And so, for example, let's just use example 1. If I were to take this pyramid and put it together with this square-based prism, notice I will get this composite object. And so I'm going to say plus equals. There we go. Now, what you'll notice about the way they've got this organized in the booklet here is they've shaded this base and this base. And you might be going, oh, well, you did that in the last lesson because you were showing us that the base area times the height is the volume. So that's why the bases are important. But actually, that's not why they're shaded this time. Notice that when these two objects are glued together to make this object, the two shaded faces aren't surface anymore. I was trying to underline that. There. Notice that these two faces here are no longer part of the surface. So how does that affect how we calculate them? Well, this area plus this area equals that area. Now, some people would probably argue, well, I'll just calculate this entire area, add it up, and then minus those two squares. That seems a little bit like more work than I'd like to do. I'd much rather kind of reason this out. There are 4 triangles here, but there's no square on the bottom. This is 4 rectangles and 1 square, right? And those shapes together will give me this composite surface area. Everybody get where I'm getting it from? 4 faces make the rectangles going laterally up, 1 square that it's sitting on, 4 triangles that are around this object, and notice that that would give me my composite surface area. So let's actually calculate that. That's going to be 4, and remember that a triangle is base times height divided by 2. And of course rectangles are length times width. So let's put in the numbers now. And let's simplify. 4 divided by 2 is just 2. So 2 times the base, which is 10, times the height, which is 9. And then over on the rectangles, they're all 10 by 11. And let's see, do I need a calculator for this? I don't think so. 9 tens is 90 times 2 is 180. 10 times 11 is 110 times 4 is 440. And when I add that together, what am I going to get? I'm going to get 40 and 80 is 120, so 620. And what unit am I in? Centimeters, centimeters what? Oh yeah, it's an area. Centimeters squared. Right? Any questions on how I did that? Now that one's a fairly easy one, fairly straightforward one. Now, what about the volume? Does the fact that this face and this face don't touch the outside air and aren't surface change the way you'd calculate the volume of these two shapes and then put them together? And the answer is no. You're not losing any volume by gluing these two shapes together. What about the base? Didn't I put the base? Oh, I didn't put the base in there. You're right. Hold on. I lost some area. Thank you for being more awake than me. Plus, how do I say a square? How about I'll just say side squared. There we go. So what did I forget? I forgot the 10 by 10. So plus 100. Oh, I guess I didn't really need to erase the whole thing. Sorry, can you fix that? Thanks for being awake there. 720 centimeters squared. That's better. Okay, go back and fix that while I have a drink. My word. Okay. Now, back to my question. When we glued these two objects together, we lost some area. We lost this square and we lost that square. Do we lose any volume? And the answer is no. It's still the same volume. So the volume here is literally just the volume of the, so the volume of the pyramid, which is 1/3, times the base that it's sitting on, which is a square. So again, I'll say side squared, times how tall it is, plus, so right, that's the volume of this thing, plus the square prism, which is length times width times height, but length and width are the same thing, so why don't I just call them S? Right, length times width times height. Now those two heights are different things. Sometimes mathematicians will, if they hit the same letter, but the letter stands for different numbers, usually in a formula you think, it's the same letter, it stands for the same number. So you know what you could do is you could add what we call a subscript to it. You could say a little p and a little r, or actually, yeah, p and r. Unfortunately, the words I was going to use both start with the same letter. But P for pyramid and R for prism. Get it? Pyramid, prism. Or you could say that you could call this shape A and shape B, and then this is the height of A, and this is the height of B. See? Math and science, folks, we like to communicate using symbols, so that and those symbols should have meaning that we're not going to mix up when we're looking at our different objects. Notice the S's are the same, right? Because this side length here and this side length here have to be the same. Well, they better be, or else they won't glue together to make this single object. All right. Now, I'm actually missing one of these numbers. What do I not know? I actually don't know the height of the pyramid. Right? The height of the pyramid is not 9. 9 is the height of this triangle. I need, let me do it in red, I need that length there, correct? So we're going to have to find that height. I called it h of a. How am I going to find it? Well, if I keep going from here to here, I have made myself a triangle. Let's redraw that triangle down here where we're working. We have this height that we're looking for, which I called h of a. It makes a right angle, and then it met with this dotted line that we already knew was 9. It was 9, wasn't it? Yeah, it was 9. And we've asked this question a couple times. What do I know about that line down there? How long is that? And I keep asking this because, you know why I keep asking this? Because this is always a mistake somebody makes when we test it. Somebody's always going to look at that and go, slap a 10 on that. It's not 10. How long is this line? And again, for those of you who are having a hard time seeing, I'm talking about this line right here. It has to be half of 10 or else this isn't the kind of pyramid I can calculate. So it's got to be a 5. So, let's try that again. H of a squared plus 5 squared is equal to 9 squared. H sub a squared is equal to 9 squared minus 5 squared. H sub a squared is equal to 81 minus 25. So H sub a is equal to, let's see, what's 81 minus 25? Well, 80 minus 20 is 60, and 11 minus 5 is, what is 11 minus 5? 6, so that's 6, so 76? No, not 76, 56? That's what I meant to say. Right? 56. And square rooted. And once again, I don't like to actually punch the square root. I know that I'll just do that when I do the big calculation. Okay, I know all my numbers. I'm ready for a formula now. 1/3 times the S is 10, remember, so 10 squared, times the number I just calculated, plus the area of the base of the prism, which is again 10 squared, times how tall the prism is, and I've already forgotten. How tall is the prism? Oh yeah, 11. And that will be the volume of the whole thing. I don't think I would punch all those buttons. I'm not going to punch 10 squared. I know that's 100. So I think I'm going to go 100 times the root of 56 divided by 3 plus, I'll just put 11 and then put 2 zeros on it. There we go. That's the buttons I'm going to punch. And I don't have the answer key, so I'm going to just punch buttons. 100 times the square root of 56 divided by 3 plus 11 with 2 zeros. And there we go. Rounded to 2 decimal places. My volume is 1,349.44. And what unit are we in? Units matter. You're going to lose a half mark for units if you don't put them. Centimeters squared. Yes, you're allowed a calculator, obviously. I'm not going to do a calculation like that without a calculator. Yes. Next test. You're allowed a calculator for part of it. For this part, you are definitely allowed a calculator. Okay. For the radicals part, you are not. So there'll actually be 2 separate files on EDSB. You'll finish one, and then you can take out your calculator and do the other. That's how we'll test it. Okay. Any questions? Okay, questions, comments, concerns? Okay, let's try the next example. Next example is pretty much the same thing. More of the same, I will say. And then I'm going to have to, you know what, then we have actually 2 more examples in here, then I'm going to make one up. Because there's one type of example that pops up all the time that they didn't put in the notes for some reason, and I really want to make sure. Did I not put a cubic on that? I just lost half a mark. No! That half mark was going to get me into Harvard Medical. Okay, there we go. So now, thank you for noticing that. Let's find the surface area. Once again, that shaded spot and that shaded spot are not going to be surface area because they cover each other up and they're in the inside, not the outside. So normally, I'm going to just, you don't have to write this down. Normally, the surface area for a cone is pi r squared plus pi r s, right? That was the formula that we did just the other day, right? Pi r squared plus pi r s. And let's see. I did use s in the formula, didn't I? This is how good my memory is. We just did this yesterday. Did I use s for slant height yesterday? I think I did, right? Somebody want to make sure, double check that I used s yesterday. I want to give you 2 different formulas in 2 different days. Did I use s yesterday, guys? That's how good my memory is. And I can't find where I wrote it down. Ugh. I think I did. I'm pretty sure I used s for slant height, right? Okay, anyway. It's pi r squared plus pi r s, right? That is the surface area of a cone formula. But look at the cone I've got. The cone I've got, I don't want to calculate the shaded part. So what do I do about my formula? Any ideas? You could turn on your microphone and tell me if you don't want to type it. What do I do with this formula if the cone I'm calculating doesn't have a bottom? What do I do with this formula? Any ideas? Really? Nobody can see this? So I have a cone. The surface area of the cone is this formula. Try to remember, we talked about when we learned this the other day, 2 days ago now. Or actually more than that, a few days ago now. We learned kind of where this formula comes from. Correct. Somebody in the chat just said, just don't do the pi r squared. This part here is that part of the formula. So I am going to add the total surface area here is the area of this cone part, which is pi r s. Now let's go to the cylinder. The cylinder surface area, again, you don't have to write this down, is 2 pi r squared plus 2 pi r h. What part of that formula do I change because I'm not doing this rooftop here? If you understand the formula, you know which part to make go away. Any ideas? I think somebody answered this question the other day when we were talking about this. So I think I've asked this question before. Okay, I'm going to do meeting attendance while you think about that. Somebody in the chat tell me, what am I changing about this formula? Well, I print attendance. There, attendance printed. Back to the chat. What changes about this formula, which is the formula of a cylinder, if it doesn't have a top? There it is. This 2 goes away. Because remember, why is this 2 here? Because pi r squared is the area of a circle. There's a circle on top, there's a circle on the bottom. But if I don't have a top, I don't need this 2. So there's the formula. So it's pi r squared plus 2 pi r h. And now we put in the numbers. I think I have everything I need, right? I have pi times radius times my slant height plus pi times this radius, which had better be the same, plus 2 times pi times 3 times 6. Now, I could ask you to answer this question without a calculator and leave the answer in terms of pi. So you might actually see a question like that. So I might want this in terms of pi. So what does that look like in terms of pi? Well, 5 threes is 15, so that's 15 pi. 9 times pi is 9 pi. And 2 times 3 is 6. 6 times 6 is 36 pi. So think of those like they're x's. That's okay. So think of those like they're x's. 15x plus 9x plus 36x. 9 plus 36 is 45. 45, 55, 60. This is equal to 60 pi centimeters squared. And if I wanted my answer in terms of pi, that's perfectly good. That's my final answer. But it does say to the nearest 2 decimal places, and 60 times pi is 188 point, what do we want, 2 decimal places again? 2. So 188.495, but when I round that to 2 places, it'll be 188.50 square centimeters. And yes, the 0 has to be there. We've had that conversation before, right? Okay, just like in the last example, volume's easier. I don't have to worry about sides that suddenly disappear because I glued them together. This one's actually a bit easier. So volume is just the volume of the cone, which is 1/3 pi r squared h plus, and again I'll say h of the cone, plus pi r squared h, and I'll use y for cylinder. So cone, cylinder. Again, these two objects have the same first letter. Oh well. Problem though, once again, do you see the problem? I don't know this number. Right? Look at the picture. They didn't tell me how tall it was. So once again, I'm going to have to find that height from the fact that the radius is 3. The radius is 3, isn't it? Yeah, the radius is 3. And the slant height is 5. And I just drew that really terribly. There. So h squared plus 3 squared equals 5 squared. H squared is equal to 25 minus 9. H is equal to 25 minus 10 is 15, so minus 1 more is 16. So 25 is, so square root of 16, so H is equal to 4. And some of you might have realized, hey, that's a 3, 4, 5 triangle, but okay, cool. Anyway, that's the height that I want. I should maybe call it H sub C since I gave it a nickname, H sub C. So I'm ready. I now know all the numbers. I'm ready to run with my formula. 1/3 times pi times 3 squared times 4, which is the number I just figured out, plus pi times 3 squared. And they told me the height of the prism, right? Yeah, the height of the, or the, not the prism, the cylinder, right? Yeah, the height of the cylinder is 6 times 6. Okay, once again, I think I'll get an answer in terms of pi. Hey, advanced techniques here. 3 divides into these two 3's and cancels the squared. So this is 12 pi plus 9 times 6, 54 pi's. So volume is equal to 66 pi's. And oh, I guess I should put a unit on that. And again, if they said, are we in centimeters? Yeah, we are. Centimeters cubed. And if we wanted the answer in terms of pi, we'd be done and we didn't need a calculator. But if we need 2 decimal places, then we are going to let you use a calculator to find it. 66 times pi's. 207 point, I'm going to say 35 when I round it. Any questions on how I did that one? Okay, there's one more that they've given you, and then I'm going to give you one. And this is going to start feeling repetitive. Good, if it's repetitive, that means it's making sense to you. That means you're getting it. But notice this one kind of has a lot of sort of similar characteristics, right? So the surface area here is, well, we've got ourselves a hemisphere. Remember that? Now the hemisphere, again, had a formula. The surface area of a hemisphere was pi r squared plus half of a full sphere, which was 2 pi r squared. And then we decided, oh yeah, we can add those together and make that 3 pi r squared. But wait a minute, problem. This part isn't part of the surface, right? This circle at the bottom isn't actually part of the outside of the shape. So it's not a 3, it's just a 2. So my surface area in total is 2 pi r squared. That's this part. And then plus, and just like I did in the one above it, I want the cylinder's surface area, but I don't need 2 circles. So it's 1 pi r squared plus 2 pi r h. And this part is for this part. Does the logic of how I made that formula work for you? When we test you on this, if we see a question like this, you're going to say, hey, I don't have written down what the formula is for a cylinder with a hemisphere on top of it. And I'm going to say, good, because nobody in their right mind would memorize that formula. You're going to just make it yourself based on formulas that you already know and understand. So, surface area is, now I think I have all the numbers I need, right? 2 times pi, radius is 18 squared, plus pi times 18 squared. Sorry, I wrote that really bad. Let me fix that. Pi times 18 squared, plus 2 times pi times 18, and the height of this thing is 32. Okay, I don't think I'm going to try simplifying that without a calculator. It gets kind of big. I have no idea what 18 times 32 is. So, we punch buttons. Come on, calculator. Oh, calculator's looking a little bit fuzzy there. Hang on. Clear. There we go. So, 2 times pi times 18 squared plus, I guess I could have said 3 pi 18 squared, but okay. I already started punching buttons. Pi times 18 squared plus 2 times pi times 18 times 32. Ta-da! Big number. 6672.74. 6672.74 cubic, no, sorry, square centimeters. This is the surface area. Okay? Now, any missing numbers in this one? You might be thinking, oh yeah, we got the same problem we had in the other 2 examples. We don't know this height. Okay, I want you to think about it. How do you figure out that height? Wait a minute. Do I need that height? This is a radius. What makes a radius a radius? It's the same thing all the way around. Oh yeah, there is no missing height in this one. This one's a little easier than the last 2, to be honest. I don't have an extra calculation on this one. I'm ready to rumble with the formula. So what was the formula for volume again? Volume was, for a hemisphere, 2/3 pi r cubed, right? Because a full hemisphere is 4/3, so you just cut that in half for a hemisphere. So 2/3 pi r cubed, that took care of, again, let me shrink this so you can see them both. Oh, hang on. My highlighting went away. So that's this part, plus pi r squared h. And that's this part. Any questions on how I got that formula? All right. Next, we put in the numbers. 2/3 times pi. Now, where's my radius? 18 cubed plus pi times 18 squared times 32. And then once again, I don't know what that is. I'm going to punch buttons. So, erase, 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 erase. 2 times pi's times 18 to the power of 3. That's how I do powers of 3 on my calculator. Oh, and don't forget divided by 3. Divided by 3 plus pi times 18 squared, I have a squared button, times 32. Okay, let me just double check that that looks right. 2 pi 18 cubed divided by 3 plus pi 18 squared times 32 equals 44,786. 44,786 point. We wanted 2 decimal places. A 5, then a 4. A 5, then a 4. And that's centimeters cubed. Okay. Any questions on how I did that one? So that's the last example in the booklet. I want to do one more. If the back page of your booklet is a blank page, then you could just write on the blank page. If you need to grab a piece of loose leaf or something, grab a piece of loose leaf. But I'm going to do one more. Notice what your booklet doesn't come across is, so we'll call this example 4, is what if you have a shape that doesn't completely cover the surface of the other shape? Like, for example, what if I stuck this cylinder, pretend those are straight lines, okay, onto this box, or rectangular prism. And I'll give you a minute to draw this. And I know you don't have the artistic skills that I have. Oh, someday if you work hard and practice, maybe you'll be as good a drawer as I am. There. Should be no gap. This distance between this solid line and this dotted line should be the same all the way across. We're going to assume that this thing is all right angled. These lines aren't crooked. Just my drawing is a little crooked. And I guess we're going to need some numbers on this thing, right? So let's see. Let's put some numbers on it. Let's call this thing 30 centimeters. Let's call that 16 centimeters, a little more than half. Let's call this thing, say, 9 centimeters. How about that? Let's call this 2B thing here 15 centimeters tall. So maybe I'll even put a line from there to there. And, of course, we need a radius. So let's put a radius on there. If that's 15, this looks like maybe 5 centimeters. There. Okay, I'll give you a sec to catch up to me and label your diagram. And then we'll calculate this, and then we'll let you guys work. Okay, so I'll give you a sec to catch up to me. At this point, I so miss having a class. I like to walk around the class and see whose diagram looks better than mine. There's always a few that look better. And then there's the kids who laugh at how bad my diagram is, almost never make a better one. All right. We ready to keep going? Okay, do you see the problem on this one? This circle here isn't really... Oh, we're going to do both. The question in the chat is, are we doing volume or area? Oh, we're going to do both. And the hard one is, again, area. Because notice that this part that I shaded yellow isn't surface, right? There's no space, there's no gap. If I had this thing glued together and I dunked it in paint, and then I pulled it apart again, the part that's yellow wouldn't have that paint color. It's not surface. So if that makes sense to you, you're probably already thinking, oh, now we're going to have to calculate areas and minus the parts that are holes. And I'm here to tell you, no, you are not. You do not have to minus anything. Why don't you have to minus anything? Well, because isn't it logical and reasonable to you to think that this circle here that I color blue is exactly the same as this yellow circle that is covered up on the rectangle, right? Like you can think, if you like, of this rectangle here. I'm going to put a check mark on that rectangle. Let's take a bird's eye view. If you were looking straight down at this object, it would look like this, right? Oh, hang on. It would look like this. And I just shaded that part blue, right? Okay. So it's like a rectangle with a circular... Yeah, that's a circle. It's a rectangle with a circular hole in it. But that hole is exactly the same as this circle. So I actually don't have to calculate any missing circles. Okay, so this little piece of diagram's in my way. Let me get rid of this. And yeah. I don't know what I'm doing wrong. I just wanted to delete that. There we go. Cut. There. Oh, it still didn't work. There, we erase. Oops. Oh, erase. Okay, so this object is made up of this piece here, which is, remember, 2 pi RH, which I'll do with, let me get a different color here. Let's see, what have I not used? I haven't used this lovely green. So this part of the formula here is this surface right here. Right? Plus the rest of the surface, which is the surface area of a rectangular prism, which is 2 length times widths plus 2 length times heights plus 2 widths times heights, or whatever. I don't really care how you give me that formula, as long as you understand that you have 3 different rectangles and you have 2 of each of them. And I'll just, for sake of consistency, I'll call that one length, I'll call that one width, and I'll call that one height. Okay? And all of these areas, I'll color them, let's see, what color can I use here? I'll color them this lovely light pink here. So this lovely, oh, that's kind of a darker pink than I thought it was going to be. So this pink here is all of the faces of the rectangular prism, and it's this circle, which now I realize that's not going to look pink by the time I'm done with it. Let me get rid of the blue. Oops. There we go. And pink. There we go. That is here. This pink area includes that circle. All right, moving right along. The surface area is 2 times pi times 5 times 15 plus 2 30 by 16s plus 2 30 by 9s plus 2 16 by 9s. Why did I pick such big numbers? Okay, so this is 150 pi's plus 3 16s is 48 with a 0. 480 doubled, 960. Somebody could double check my mental math. 30 times 9 is 270, doubled is 540. Plus, what's 16 by 9? Is that 144? That's 144 doubled is 288. I better double check that math. Make sure I got that right. 16 times 30 times 2, yeah, 960. 2 times 30 times 9, yeah, 540. And 32 times 9, 288. Yep, we got it. Okay, so add all that together. 960 plus 540 plus 288. If we were being asked to leave our final answer in terms of pies, it would be 150 pies plus 1,788 centimeters squared. I'll do the same thing we've done in the other examples, and I'll get that to 1 decimal or to 2 decimal places. So plus 150 times shift pies. And there we go. 2,259.24. And you know what? I've actually changed my mind. Do we care about the volume of this one? Is there any trick to the volume on this one? No. The volume on this one's just a cylinder plus a rectangular prism, right? You don't have to worry about considering where you've, lost a circle on the bottom but replaced it with the circle on the top. None of that stuff matters when you're doing volume. Volume is easier than surface area. Now, I am going to stop at that example. At this example, hopefully I've managed to convince you that you don't have to worry about subtracting any areas because they're being covered up by other areas. If you, again, dunked this thing into paint, and say you took a little piece of paper and you glued it onto here. Well, when you took this thing apart, when you removed this cylinder from the box, you'll be going, oh, there's a white circle here. Well, take this piece of paper off of there, and it should exactly cover the circle that's missing. So it's like it's the same area. Hopefully that little story or analogy makes sense to you. Now that's for this example. If we ever gave you an example where, for example, suppose we stuck a cylinder on top of, say, another cylinder, and then stuck that on top of yet another cylinder. And boy, did I ever draw that terribly. Can I start that over? Yeah. Let me try that again. Suppose I took a cylinder on top of another cylinder on top of another cylinder. I think I won't bother with the dotted lines. I'm still drawing that terribly. It makes I'm making it look like it's going inside. I don't want it to look like it's going inside. I'm going to draw it like that, and then like this. There we go. That's what I was looking for. There. Suppose I had something like that. I have a cylinder that's kind of medium sized sitting on top of a little cylinder, which is sitting on top of a bigger cylinder. Now, what would you do for surface area? Well, now you'd have to do some calculating where you're subtracting things, right? Because this top part is just a circle, but this bottom part is a circle with a hole that's this big right here, right? And this area here wouldn't be replaced by another part the way it was in the previous example. So, if you see one like this in your homework, you'd have to do a little more thinking. And hopefully nobody be going, quick, what's the formula for a cylinder on top of a cylinder on top of a cylinder? That's not the way this stuff works. This is like playing with Lego, where you're going to build your little spaceship out of the other little pieces. I built this formula here out of the pieces of what I needed from formulas that I already know. The formula for a cylinder and the formula for a rectangular prism. Okay, so I'm going to stop the lesson there. I think that's pretty much all I wanted to talk about. Okay, so let me close my video. Thanks for watching it.